So let us start for today's class. Today is the fifth week of the tutorial session for the course Technologies for Clean and Renewable Energy Production. So let me share my screen first. My slides are visible.
Yes, ma'am.
Okay. Okay. So today is the fifth tutorial class for the course Technologies for Clean and Renewable Energy Production. So the content for today's class, sorry, today's class. Uh, Till now, as we have studied, as we have discussed about the energy production from coal and petroleum. Coal is basically solid fuel and petroleum is liquid fuel. So now we will be talking about, in this week, we will be talking about the various gaseous fuels. So we will be talking about gaseous fuels and their types, then their properties, then the some of the naturally available gaseous fuels, their applications in different uh, just a minute. Their applications in heat and electricity production and various chemicals and hydrogen production. Then various routes which are used for reforming these gaseous fuels. Different types of reforming we will be studying about. Then we will also be talking about why we need to convert this gaseous fuel into liquid fuels and some of the important routes with using which we can convert these gaseous fuels to liquid fuels, which are such as FT synthesis, then methanol synthesis, then DME synthesis. And we will be also, and in the last section, we will be talking about the uh, production of hydrogen from these gaseous fuels. Firstly, we will be talking about the production of syngas from these gaseous fuels, which naturally produce gaseous fuels, how to convert these naturally produced gaseous fuels to syngas, and then how this syngas can be used to produce hydrogen. As we all know that hydrogen is a very nowadays it is a very trending kind of fuel, as it is a green fuel. It produces energy without carbon emission. So different routes to produce how to produce hydrogen and different routes we will be talking about, that is reforming and decomposition of methane. Mean two forms how we can produce hydrogen from syngas. So let us start. So, firstly, coming on to what are gaseous fuels? As we have talked about earlier, both about the solid fuels such as coal and the liquid fuels, that is petroleum. So, third kind of fuels are that are naturally available, that are naturally produced from the earth crust, are the gaseous fuels. And these gaseous fuels, as the name itself tells, it is gaseous in nature and it burns in air to release heat. And this heat can be used to generate electricity, also to generate steam, which can be further used in steam turbines to generate electricity and various other uses also. So it is, these gaseous fuels can not only in the form of gases, but it can also be used by converting them into liquid fuels. So we will be talking about it later, why we want to convert, why we want to change these gaseous fuels into liquid fuels, that we will be talking about it in later in the class. So different type of gaseous fuels. So some are available in the nature. Some gaseous fuels which are available in the nature is natural gas, NG is a natural gas, CNG compressed natural gas, liquefied natural gas, then coal bed methane, gas hydrates. We will be talking about all of them in detail in the class in today's class. Then some of the gaseous fuels which are produced from solid fuel, that is coal. Basically, solid fuel, they are produced from coal, that is water gas, producer gas, as we have studied earlier, then coal gas and town gas, and syngas also. We have talked about it earlier that how to produce syngas from coal. Now, some of the gaseous fuels which are produced from liquid fuels, the liquid fuel, just a second, someone wants to join. Then some of the gaseous fuels which are produced from petroleum, which is the liquid fuel we have studied in the last week. Then the liquid gaseous fuel produced from liquid fuels mean from petroleum, it is LPG, then the refinery gas. And some of the gaseous fuels are also produced from fermentation, that is basically from the bio waste. Bio waste means biomass, that is the rejects from animals such as cow dung, etc. Biogas is produced, landfill gas is produced. So we will be talking about all of these in detail today. Coming on to the composition of various gaseous fuels. The first one is natural gas, which consists of methane 92%, then some amount of hydrocarbons 5%, mean other hydrocarbons, then inerts 3%, and LPG mainly consists of propane and butane 20% propane and 80% butane. Then coal gas also consists of hydrogen, carbon monoxide gas, methane, then carbon dioxide, and producer gas. As we have studied, it mainly consists of carbon monoxide and hydrogen, along with it, carbon dioxide and some other hydrocarbons as well. And syngas mainly consists of carbon monoxide and hydrogen, as we have studied, but some very lower content of carbon dioxide and some hydrocarbons as well, and some amount of nitrogen. And water gas consists of hydrogen, mainly hydrogen, then carbon monoxide gas, some amount, and then some saturated hydrocarbons and unsaturated hydrocarbons are also present. And all these gaseous fuels, their heating value is shown here, which shows clearly that LPG has the highest heating value, followed by natural gas and all others which have lower heating value. Coming on to some of the properties of these gaseous fuels. The first one being density. So as we know, density, as we all know, density is mainly mass upon volume. But here we are talking about the relative density, that is the dimensionless density. So as we are talking about gaseous fuels, so we will be taking it in relation with density of air. So density of our gaseous fuel with respect to the density of air. Then another characteristic is Bobbe number. It is basically the gross calorific value, which is also the higher heating value as we have studied during our coal classes. It is the higher heating value uh, upon relative density of air to the power zero point 0.5. So what is basically Bobbe number? The Bobbe number is a characteristic. It is a characteristic of fuel, of a gaseous fuel, which tells basically the amount of energy, amount of heat generated from per volume of a gaseous fuel. So suppose if we have a mixture of gases, different gases such as natural gas, water gas. If we have a mixture of gas to produce energy, and if we want to replace any one gas in that mixture with another gas. So how we can replace? We can replace another gas containing the same Wobbe number, almost relative Wobbe number. If another gas has the similar Wobbe number, then we can replace that gas with another gas. As this will ensure that by adding that gas and removing one component and adding and replacing it with another, It will ensure that the amount of energy, the desired amount of energy that we want, the desired amount of heat that we want from that mixture of gases is unchanged. Another characteristic is temperature, or temperature of dew point and moisture. It is basically the dew point we are talking about. It is basically the dew point is, as we are talking about the gaseous fuel, it is the minimum temperature at which the hydrocarbon present in the gaseous, mean the different hydrocarbons present in the gaseous mixture starts to condense. So basically, if we have a mixture of mixture of gases, and we it is basically in the dew point. Basically, we are talking about the hydrocarbon dew point. It is basically the temperature at which the hydrocarbon component of any hydrocarbon rich gaseous mixture it starts to condense. Another characteristic is explosibility limit. It is basically the gaseous fuel we are basically using for to generate heat or generate energy. So we need to burn them. So explosibility limit is basically the, any fuel it starts to burn only when three conditions are fulfilled. So basically, it requires oxygen. Is happening today. Just a second. Can you guys give me a minute? Just a minute. Basic requirement is it should have appropriate oxygen. Then a fuel is required and a heating source is required. So if any one of them is missing, any single component is also missing, then the combustion or heating or the burning will not begin. So explosibility limit is if we have over the limit or under the limit amount of fuel, then it will not burn. If we are having excess oxygen, if we are having excess fuel, then also proper combustion will not occur. And if we are having less amount of fuel uh, below the lower limit, lower explosive limit, then also our explosion or our burning of the our combustion will not take place. So before a gas or explosion can occur, three conditions are required, as I've told. Basically, oxygen is required, then a fuel is required, and thirdly, a ignition source, a spark or flame is required. Just a second, guys. My pen is not working. Okay, let me teach without it. Okay, then. So basically, the reach. Sorry for the inconvenience, guys. It is a bit disturbing because my pen tab is not working properly. Okay, now let's start. So basically, what I'm telling is that if the amount of fuel is less or in excess, proper combustion will not take place. And for that, there is a limit. The minimum concentration of a particular combustible gas or vapor necessary to support its combustion is the minimum amount, the minimum concentration which we require of a fuel. It is called the lower explosive limit. And the maximum concentration and the maximum amount that after that, if you will add the fuel, then also proper combustion will not take place. So that is called the upper explosive limit. So the next property is stoichiometric air. It is basically the air fuel ratio which we require for a proper combustion. So air fuel ratio also determines whether a mixture is combustible or not. So basically, after some empirical calculations done, it is calculated that air fuel ratio for a proper for a air fuel ratio of 14.7 to 14.7 is the optimum air fuel ratio. If it is less than that, then combustion will not take place. And if it is more than that, then we can say that excess air is provided. But it is found that this exact ratio does not give a optimum performance. So that is at least 5%. If we add 5% excess air, then optimum performance or optimum combustion takes place. The next characteristic is octane number. This we have studied earlier also. It basically is the measure of anti-knock property of a fuel. So it is basically seen by the mixture of isooctane, uh, calculated by a mixture of isooctane and N-heptane. So if we have to calculate the octane number, what we do is we take a mixture, a mixture of we take this mixture and compare it with a isooctane and N-heptane mixture, and at what concentration of isooctane and N-heptane the performance of the given fuel and this isooctane and N-heptane mixture performance matches, then the ratio of isooctane is basically the octane number. Then talking about the naturally available gaseous fuels, they are basically, as I told earlier, that basically it is liquefied natural gas, compressed natural gas, and gas hydrates, coal bed methane. So we will be talking about all of them. So basically, natural gas is can exist in lithosphere separately, or it can accompany the oil, basically the crude oil, petroleum we are talking about. It can be present either along with it, or it can be present separately also, or either it is diluted in oil or diluted in water, which we basically call it gas hydrate, and diluted in rock, it is basically the coal bed methane. So coal bed methane, it is basically the gas, it is basically the methane gas which gets absorbed into the coal under great pressure. So it is basically the methane gas only which is absorbed in coal under great pressure, and the mine methane and its concentration is basically 96% methane and 3% nitrogen, and some of other components are compounds are also present. So basically, what we do is we during mining, the pressure in the coal field, it when the pressure in the coal field it is released, then the absorbed gas also undergoes desorption and it evolves out. So basically, when the pressure is released, along with that, this coal bed methane is also released. So mine methane, it is collected in steel. It is collected in steel pipelines and transported from the mine. Due to the pressure applied, the mine methane has a considerable. Due to all this pressure and all this evolving procedure of this coal bed methane, it has a considerable content of air, which is about 20 to 50% of air. Just a second. Trying to join. Another next type of uh, gaseous fuel is gas hydrates. So basically, these are the methane gas along with some amount of moisture or methane or some higher hydrocarbons. Basically, hydrates, these are crystalline structures consisting of combined water and gas molecules. Normally, they are in the form of water ice and given off. They are basically in the solid state, water ice form, and when heated, it gives off methane. So the content of methane is as high, that is about 1 meter cube of hydrate can give about 164 meter cube of methane. So deposits of hydrates are located in continental slopes. It is basically present in the below the sea floor. They are basically stable here. Some amount is available above the sea floor also, but it is not in that much amount. So extracting it is basically not feasible. The deposits are global resources of hydrates are estimated at 10 to the power 16 meter cube of methane. So due to climatic and geological conditions, their extraction is still not cost effective. Their extraction in a cost effective manner is still under it is still under development procedure. Coming on to applications of gaseous fuels. So various applications are of gaseous fuels are there, such as heat and electricity production, and then conversion of them into liquid fuel and hydrogen production, and application basically conversion of them into liquid fuels and various other chemicals such as methanol, DME, and hydrogen production. Basically, the first one is the natural gas on combustion gives hot flue gas, and after heat recovery from this flue gas, it produces heat, and or either it can be given off to the steam turbine where it is used for the production of electricity. Then second procedure, the this one is the conventional method, but this one is the modern method, which is after this natural gas is reformed into syngas, and conditioning and cleaning and conditioning is done to convert the syngas into various liquid fuels, chemicals, and hydrogen to produce energy. Now, this is a flow sheet of various applications from these gaseous fuels. So basically, the conventional one here, CNG is given in the combustion chamber where combustion takes place and heat is released. And here in the gas turbine, expansion of this flue gas takes place is and further it is sent to the compressor along with some air and here to the alternator to produce electricity. Further, this gas here can be sent to the turbine for where it expands and is sent to the boiler for heat recovery for heat recovery as flue gas, or further it is sent to the steam turbine where it is in turn sent to the alternator for electricity generation, and even some amount of heat is also sent back to the condenser for heat recovery. Coming on to some of the reform, coming on to various types of reforming techniques which are used as cleaner route for natural gas utilization. So basically, what is reforming? It is basically conversion of one form of reforming of one product into another product or a more useful, more desirable product. So it is basically here we are talking about the natural gas. Mainly, it is the highest content is methane. So we are talking about reforming this methane into hydrogen and carbon monoxide, which is basically the syngas by means of exothermic or endothermic reaction, depending on the chemical procedure. So it is basically it is either reforming is done either catalytic using catalyst or without catalyst also reforming can be done. The elimination of oxygen from the initial fuel mixture improves the overall system efficiency by minimizing the energy losses. So basically, oxygen is not desirable. So sometimes before reforming, oxygen is removed beforehand. Product can be used for different applications such as heat, steam, liquid fuels, and chemical synthesis. So this is the procedure. This methane is reformed into syngas, and how we will do? We will study various methods now. So different types of methane reforming techniques are available. So basically, the first one is steam reforming, then the partial reforming, then the autothermal reforming. These three are most widely used, basically the commercial ones. And these dry reforming of methane, then combined reforming of methane, which is basically bi-reforming, then tri-reforming, reforming with membrane. These methods are still under development. So let us move on to different kind of reforming. Firstly, the steam methane reforming. So as the name itself tells, steam methane. So what is done? Steam is used to reform methane. So basically, methane is taken along with steam, which is hydrogen, which is basically water. The reaction of steam and hydrogen, which gives carbon monoxide and hydrogen. Steam methane reforming. Methane reacts with uh, H2O to give carbon monoxide and hydrogen, which is here seen to be as endothermic reaction, as it is plus, so it is endothermic reaction. And further, this methane reacts with excess moisture, excess steam to give carbon dioxide and hydrogen, which is also an endothermic reaction. Then some water gas shift reaction also takes place where this carbon monoxide further reacts with steam to give carbon dioxide and more hydrogen, which is an exothermic reaction here. And the main property is basically the main condition required is that during steam methane reforming, hydrogen to carbon monoxide, which is basically, as we know that our main reactant here is syngas. So basically, it is carbon monoxide and hydrogen. So main property is the hydrogen to carbon monoxide ratio should be 3:5. Then only steam methane reforming will take place, and the temperature range in which steam methane reforming takes place is 700 to 850 degrees C, and the pressure is 515 to 30 bar. So here large amount of CO2 emission takes place. And it is an expensive method for production of hydrogen. Basically, it is also various catalysts are required. It can occur in without catalyst, but modern steam reforming catalyst, modern nowadays steam methane reforming is done in the presence of catalysts such as nickel on ceramic support with or without promoter or stabilizer. The pressure Various other catalysts are also in the search. So supports must be requirement is high geometric surface area, high heat transfer coefficient is required, low pressure drop, and less carbon deposition takes place here. This is basically a steam methane reforming reactor. What happens is these are the tubes in which hydrocarbon, which is mainly methane, along with steam, is introduced in these tubes. And outside of these tubes, heating takes place, which is also done using methane, which is by combustion of methane with combustion of methane. This flue gas is used for the heating of these tubes in which methane and uh, steam is fed. And here reforming takes place. These are basically called the reformer tubes, and in temperature around 700 to 850 is given here, as I have told here that it takes place in the range of 700 to 850. Temperature is given using this flue gas and pressure 20 to 30 bar. So we get this about 70% hydrogen in dry. Basically, steam methane reforming reactions taking place here are these we have studied before: the water gas shift reaction, which is exothermic, and the steam methane reforming reaction, which is endothermic. Now, coming on to second kind of reforming, which is partial oxidation or catalytic partial oxidation, which is POX and CPOX. So, operating condition, basically the reactions taking place here, oxidation takes place, partial, that is in the presence of controlled oxygen. So this is the partial oxidation, CH4 plus half O2, which gives carbon monoxide and hydrogen. And this is the catalytic in the presence of catalyst. Some reactions taking other reaction is excess oxygen, which gives carbon dioxide and water. And then some side reactions are also taking place, which are given here, where here in which this methane further reacts with this steam, and further this steam and carbon dioxide giving carbon monoxide and hydrogen. So basically, these are two side reactions. It is an exothermic process, faster than steam methane reforming, and requires a smaller reactor vessel, which is a plus point that it requires a smaller reactor vessel. And the main reaction taking place is this one, the first one. This reaction is the main. In the heat released is minus 36 megajoule per kilomole, which is basically showing that it is an exothermic reaction, and hydrogen to carbon monoxide ratio is 2 to 2.5, and temperature range is 1200 to 400 degrees C, and higher pressure of 50 to 70 bar. And catalysts used are basically the transition metals, nickel and cobalt, and precious metals such as ruthenium, rhodium, palladium, platinum, and iridium. So basically, carbon deposition is a major issue here. It is basically what happens is during this reforming, carbon deposition starts to take place on the catalyst, thus deactivating the catalyst. This is a POX and CPOX reactor. What happens is we introduce the fuel basis, which is basically methane along with oxygen. And here, reforming takes place. This is the reforming zone. And further, here, heat exchanger is used for excess recovery of excess heat. And this part, in the second one, which is CPOX reactor, here, catalyst is also present. CPOX is basically catalyst partial oxidation. So, catalyst is also present. We introduce the methane and oxygen, and here, in the presence of catalyst, reforming takes place, and further in this zone, excess heat recovery takes place. The third one is autothermal reforming reaction. So basically, this is a combination of both steam methane and partial oxidation reaction. So first one is steam methane reaction, which is methane in the presence of steam, and the second one is in the presence methane in the presence of oxygen, which is basically partial oxidation reaction, and this is steam methane reforming reaction. Hydrogen to carbon monoxide ratio should be about 2, and temperature is in the range of 850 to 1000 degrees C, and pressure is 220 to 100 bar. And the catalyst used are mainly nickel-based catalysts. So basically, what happens is there are also two zones in a ATR reactor. First one is the combustion zone, where the a FOX reaction takes place. Basically, the partial oxidation reforming takes place, which is in the presence of oxygen, as we have studied earlier. So here, combustion takes place. As we can see, this is a exothermic reaction. So this heat is further used in the SMR reaction, as we know that SMR reaction is endothermic, so it requires heat, external heat. So this heat is provided by this FOX, heat released by the FOX reforming reaction. So here FOX reforming reaction takes place, and here SMR reaction takes place, and heat released here will be used here. So by proper adjustment of oxygen to carbon and steam to carbon ratio, the partial combustion in the thermal zone supplies the heat, as I have told. Partial combustion here supplies heat to the SMR reaction. The product gas composition at the exit of the reactor results very close to the thermodynamic equilibrium of the adiabatic reactor. The next one is dry methane reforming. It is basically DMR, dry methane reforming. It is written down. So dry methane reforming, in this, methane reacts with carbon dioxide to give carbon monoxide and hydrogen, and it is an endothermic reaction. Hydrogen to carbon monoxide ratio is 0.4 to 1.5, and temperature is in the range of 630 to 850 degrees C, and pressure is 1 to 20 bar. So presence of carbon dioxide gives rise to more chances of carbon formation. So here carbon formation is more, and catalyst uses nickel based catalyst. So basically, the problem here also is the carbon formation, which deposits on the active catalyst material, thus degrading it and thus making them inactive. So the removal of this carbon is the main challenge. Next one is bioreforming. In this bioreforming, name itself tells that two reforming reactions takes place. Basically, the first one is steam methane reforming, that is CH4 plus H2, which gives carbon monoxide and hydrogen. Then further, it also gives carbon dioxide and hydrogen if excess steam is taken. Then the second reaction is carbon monoxide with carbon monoxide also reacts with steam to give CO2 and hydrogen. And then this methane again reacts with carbon dioxide to give carbon monoxide and hydrogen. This is basically the trimethane reforming reaction, as we have seen here. Here methane reacts with carbon dioxide. So this is a mixture of trimethane reforming reaction and steam methane reforming. So it is overall an exothermic reaction. H2 to CO ratio is required is 2, temperature is 700 to 950, and pressure is 10 to 30 bar. And catalysts are mainly in all the reaction. It is nickel-based catalysts are commonly used. Some other catalysts are also used, such as nickel zirconium, nickel alumina. But but nowadays we are trying to use nano catalysts, nano particles as catalysts, which is seen to give a better performance. The third one is tri-reforming. It is basically, the name tells, three reforming reactions takes place, as it is shown here: CO2 reforming reaction, then steam methane reforming reaction, and methane oxidation. So it is basically methane plus CO2, then methane plus H2O, then methane plus oxygen, as it is shown here. This is the methane oxidation reaction, methane CO2 reforming reaction, then steam reforming. And it is overall an endothermic reaction. It is, as it is shown here. Temperature is required is around 1000 degrees C. Pressure is 20 bar, and hydrogen to carbon monoxide ratio required is 1.2 to 1.5. And the catalyst used are here also nickel-based catalysts. Some examples are nickel, calcium oxide, zirconia, nickel CO2, Le2, O3, etc. And such more catalysts are used. Am I audible? Hello.
Yes, ma'am.
Okay. So now coming on to why syngas is required to why syngas needs to be converted to liquid fuel. So basically, we if we convert syngas to liquid, mainly the simplest reason is to meet the market requirements, as liquid fuels are much easier to handle, and in various transportation vehicles, etc., liquid fuel is much easier to deal with. So one reason is that, and the second reason is that the liquid fuel has more energy density compared to gaseous fuels. So basically, that's why these are some of the conventional requirements that uh, this is the new technology. So in this, basically, what is done, gaseous fuel is converted to liquid fuel, and liquid fuel and various other chemicals as well for using it in transport fuel market. So basically, the first thing that we will be studying here is the conversion of this syngas into the lighter, the lighter liquid fuels, basically. So in the previous classes also we have studied about Fischer-Tropsch reaction. So what happens is the syngas, it is converted to wax, naphtha and diesel, which are further upgraded. This wax is then hydrocracked to produce diesel and other products. So main reactions taking place in Fischer-Tropsch reaction, as we know, syngas, it is carbon monoxide and hydrogen. So when this syngas reacts to give a hydrocarbon chain, it also reacts to give paraffins, olefins, and water gas shift reaction takes place. So basically, it is an overall exothermic reaction. So what happens is in the flow sheet we can see the syngas is given to the Fischer-Tropsch reactor. So here reaction takes place in the presence of moisture, in the presence of temperature and pressure. So what happens it is the heavier wax is given from below and the lighter waxes are given from above, and here it is separated into more lighter products which are given here, and the uh, further such as of gases. Of gases, and the lighter wax is given from below, and all this wax is further hydrocracked. As we have studied, hydrogen is required for hydrocracking. This wax is hydrocracked to give if the to give lighter products, which on introduction in the distillation column gives various products depending on their different boiling points. So naphtha is given, kerosene is given, then diesel, etc., are given, which can be further used in various transportation vehicles. And if there are some waxes left, which they are again flushed back into the hydrocracker for further hydrotreating. And if some amount of lighter gases, off gases are also given out, which can be used for combustion or for heat recovery, etc. So the various uh, reaction conditions required for Fischer-Tropsch reaction is hydrogen to carbon monoxide ratio required is 2 to 2.2. Then pressure required is 5 to 30 bar, and temperature it takes place in two uh, ways, in high temperature range of 325 to 370 degrees C, and in low temperature range of 220 to 270 degrees C. P and gas are the so just a second. Give me a second. Sorry for the inconvenience, guys. Today my pen is not working, so it is a bit inconvenient. So GHSV is 700 per hour, and catalyst used are basically iron-based, cobalt-based, or GSM-5 supported bimetallic FT catalyst for gasoline. So basically, some this iron-based catalysts, they are flexible, they are fuel flexible. Basically, it can produce all kind of fuels such as gasoline, diesel. But this some catalysts are product specific, such as GSM-5, which is given here basically for gasoline synthesis only. So coming on to two temperature ranges. Why two temperature ranges? If if Fischer-Tropsch reaction takes place at high temperature, then the products are different. C5 cut is 50 to 80 weight%, and low waxes are very less, and gasoline to diesel ratio is 2:1, and cetane number of the diesel produced in this in at high temperature Fischer-Tropsch reaction is about 50 to 60. But at low temperature we can see that C5 cut is lower, that is 20 to 30 weight%, but wax content is very high here, that is 50 weight%, and gasoline to diesel ratio, which is higher, which is 1/2, which is basically we can say that diesel is higher, so cetane number is also higher here, that is 80. Now coming on to methanol synthesis, not only we are talking about the different fuels, liquid fuels. We are also talking about the conversion of syngas to various chemicals, which are used in various industries, also in different labs and in various commercial purposes also. So the one of the chemical we are talking about is the methanol synthesis. So it is basically here it is methane is not biomass. Instead of gasification, it is reforming, which is estrogen. Basically, this firstly methane is reformed to syngas, and then this syngas will be used for the production of methanol by by its reaction in the presence of catalyst given here, that is CuO, ZNO, or alumina, and the ratio of hydrogen to carbon monoxide is 2, and the reaction taking place here is this one. We will be talking about this in detail. So methanol synthesis, basically the reaction, it is done in the presence of copper and zinc oxide catalyst. And the reaction taking place is carbon monoxide when reacts with hydrogen, it gives methanol, and it is basically an exothermic reaction we can see here. And further carbon dioxide reacts with hydrogen to give carbon monoxide and water, and then carbon dioxide reacts with excess hydrogen to give methanol. So it is believed that firstly carbon monoxide is converted to carbon dioxide, then this carbon dioxide is converted to methanol. So basically, the hydrogen to carbon monoxide ratio we have talked about is 2. There is another value which is here required. There is this another term which is required here, which is R value. It is basically H2 minus CO2 upon CO plus CO2, which is required to be around 2, and basically due to the equilibrium constraints, the carbon monoxide conversion to methanol is limited to 25% only. And process operates at a temperature range of 220 to 250 degrees C and pressure range of 5 to 8 megapascal pressure. Another chemical that we will be talking about is the DME synthesis. Also methane, little reforming. There are two uh, ways to produce this DME, which is dimethyl ether. Either we can produce syngas methanol, firstly methanol from syngas, then this methanol is converted to DME, or we can directly produce DME from syngas. So the reaction taking place, it is reaction taking place in a direct route is this. And as we have seen that during the synthesis of methanol, hydrogen to carbon monoxide ratio is 2, but here the hydrogen to carbon monoxide ratio required is 1. This flow sheet tells us is basically a flow sheet for the synthesis of methanol and DME. Here we take the natural gas which is reformed into syngas, basically carbon monoxide and hydrogen. Further, this syngas is introduced into the methanol reactor where hydrogen to carbon monoxide ratio required here is 2 to 2.2. Then here in the methanol reactor, when methanol is formed, this methanol is sent to the DME reactor, and if some amount of unreacted syngas is left, then it is again recycled back for further methanol synthesis. And in the DME reactor, when the reaction takes place, after the reaction, this DME is sent to the DME separator, where it is sent. The pure DME is sent from above, and some unreacted methanol, if it is left, then it is sent to the methanol separator, where unreacted methanol is again recycled back into the DME reactor, and after separation, if some amount of water, it is taken out from it. Now coming on to hydrogen as a green fuel. Basically, hydrogen can also be produced from the syngas, as we have seen basically during the syngas deformation. What we can also produce hydrogen from the natural gas, as we have seen. The syngas mainly consists of carbon monoxide and hydrogen. So basically, as we know that hydrogen is a it is becoming very popular source of energy nowadays, since it produces it's due to its higher. Just a second. Why hydrogen is a very good source of fuel? Because of its high energy density, which is about higher rating value 142 millijoule per kilogram, and it does not produce carbon dioxide. So during energy production, there is no carbon dioxide emission. So, and it can also produce electricity in using we can also produce electricity using hydrogen in fuel cell. So what happens in the fuel cell when we introduce hydrogen at the anode? It breaks into, as we can see, it breaks into H positive and an electron, which goes through the external circuit, and this H positive is transferred to the cathode through this membrane. It is basically a membrane separator, and it is transferred from the anode to cathode through this membrane. And here it reacts with the O2 to give it reacts with the oxygen to give H2O by taking this electron from the external circuit. So we can see here the electricity is generated in this external circuit. So hydrogen is produced by various types of reforming procedures, as we have studied earlier. The dry reforming procedure, in which methane reacts with the carbon dioxide, then steam reforming, in which it reacts with the steam, then partial oxidation, where it reacts with the limited amount of oxygen, then autothermal reaction, which is a combination of steam methane reforming and partial oxidation, and reforming, then tri-reforming, which is a combination of partial oxidation reforming and dry methane reforming uh, and steam methane reforming. So we can see that in all these reforming reactions, one thing is common: it produces hydrogen. So the most popular and the most used steam reforming reaction is for hydrogen production is basically steam methane reforming. And here we can see that hydrogen to carbon monoxide ratio is 3 is to 5, which is high compared to all other reactions. Coming on to this steam methane reforming, once again we will study it in more detail. So the reaction taking place, it will be methane will react with steam to give carbon monoxide and hydrogen, basically, which is our requirement here. The steam to methane ratio in feed here used is 1:1. However, higher steam to methane ratio is mostly used in industrial practices. In the SMR, it has an energy efficiency of 70 to 85 degrees C, and carbon dioxide emission here is 7 kg of carbon dioxide is emitted per kg of hydrogen produced. Let us talk about a bit about the mechanism of this steam methane reforming reaction. It is basically a heterogeneous reaction, as it takes place in the presence of catalyst. So catalyst is solid and are carbon monoxide and hydrogen, and steam, it is basically gaseous and gaseous. So basically this gas plus solid state reaction takes place, which is a heterogeneous reaction. So here what happens is the hydrogen reacts with the, suppose if we take the nickel catalyst, so the steam reacts with the nickel catalyst, yielding adsorbed oxygen. We can see here this steam reacts with the nickel catalyst. This S is basically our solid catalyst. It reacts with the steam, releasing hydrogen and adsorbed oxygen. The oxygen gets adsorbed onto the nickel catalyst. Then further, methane reacts with this nickel catalyst and releases CH2 adsorbed along with hydrogen adsorbed. Then further, this adsorbed CH2 reacts with the oxygen adsorbed, this one and this one reacts together to give CHO adsorbed and hydrogen adsorbed. Further, this CHO adsorbed, this species dissociates to give carbon monoxide adsorbed. It further reacts with the catalyst. This species further reacts with the catalyst to give carbon monoxide adsorbed and hydrogen adsorbed. And then carbon monoxide adsorbed reacts with the oxygen adsorbed to give carbon dioxide adsorbed and carbon dioxide adsorbed. Then this species again reacts with adsorbed oxygen to give carbon dioxide adsorbed and hydrogen adsorbed. So here we can see that we have got carbon monoxide adsorbed, which will be dissolved from the catalyst to give carbon monoxide. Then carbon dioxide adsorbed will get dissolved from the catalyst to give carbon dioxide, and hydrogen adsorbed will give hydrogen, leaving behind the catalyst. So this is basically a heterogeneous reaction mechanism of the steam methane reform. This is the block diagram telling us about the natural gas steam reforming plant. Here natural gas is introduced. So further, firstly, we will be doing the desulfurization. This is the natural gas from the earth crust. So basically, if it consists some amount of sulfur, we need to remove it because if a minor amount of sulfur is also present, it will deactivate our catalyst further during reformation reaction. So desulfurization takes place here. Then further heating of for this pre-methane reforming takes place. Preheating of our natural gas here takes place to the range of 300 to 525 degrees C. Then this preheated uh, natural gas is introduced along with this preheated methane along with the steam is introduced into the SMR reactor where temperature is increased to 800 to 900 degrees C and uh, here steam methane reformation takes place and further if heat is released it is taken to some kind of boiler or heat exchanger for heat recovery and further it is sent further for high temperature water gas shift reaction and low temperature water gas shift reaction. So after this shift reaction, the gases given out here are sent to the pressure swing absorber, which releases about very high purity of hydrogen, which is 99.99%. And further this, if some further this heavier gas heavier products are sent for low uh, low temperature water gas shift reaction where it is sent to CO2 first if some amount of carbon dioxide is present it is absorbed here to give 97 to 99% pure hydrogen. So what is basically pressure swing absorber? It is basically a mixture of it is a bed of different catalysts. It is a different catalyst bed as we get the gases from here, it along with hydrogen, there are many other gases present, such as carbon monoxide is also there, carbon dioxide is also there, some amount of steam may be present or moisture may be present. So, in pressure swing absorber, what happens is we take a catalyst bed which consists of different catalysts. So these different catalysts absorb these different other gases at high pressure, leaving behind hydrogen. And why hydrogen is not absorbed? Because hydrogen is very smaller in size. So it does not get absorbed. It has very high diffusivity. So all other gases, all other remaining gases such as carbon monoxide and carbon dioxide, etc., gets absorbed in this pressure swing absorber, leaving behind hydrogen, giving a very high purity of hydrogen. Coming on to another technique for the production of hydrogen, which is methane decomposition. Apart from reforming, another technique is methane reformation. This methane is cracked in the presence of heat. This reaction takes place to give carbon, solid state carbon and hydrogen. So it is basically direct production of hydrogen suitable for fuel cells or any other purpose. And here the temperature is high temperature is used that is 1200 degrees C. And carbon dioxide emission here is much lower that is 0.05 mole carbon dioxide per mole of hydrogen produced which is much lower than the reforming carbon dioxide produced. The different kinds of thermal cracking method, different methods are used for methane decomposition. The first one is thermal decomposition. So decomposition of methane takes place in the presence of heat, which is as we can see, it is taken this cracking taking place at very high temperature, and it is an endothermic reaction. But if the same reaction, the main problem with this is carbon deposition is a very big problem. As we can see, solid carbon is produced, so it gets deposited, so which is a very big problem of this procedure. Another thing is if we use this same reaction is done in the presence of some catalyst, then we can see that the temperature is reduced a lot from about 1200 degrees C, it gets reduced to about 500 degrees C. Different catalysts were used. So from about 1200 degrees C, different catalysts after using, we found out that nickel based catalyst gives our very good performance at very lower temperatures. So different catalysts for use, transition metal catalysts are used, and this technology is still in development. Another technique is plasma cracking, which is basically we know that plasma is an ionized gas which can be generated by several means such as high voltage electric discharge, flames, etc. So here cracking takes place using plasma. So two types of plasma cracking takes place. The first one when plasma is produced using high electric power or at very high temperature, that is 5,000 to 10,000, which is highly energy consuming process. So this is not feasible. Another is electrochemical plasma cracking, which is can catalyze the decomposition at lower temperatures around 350 to 750 degrees C through generation of active species. The benefit of plasma methane cracking is basically it has high thermal efficiency, about greater than 80 degrees C, then high purity of hydrogen is there, and then simultaneous production, different valuable byproducts are also produced here, and CO2 emission is very low. But this is restricted to use on the commercial level due to its high electricity usage. High electrical energy is required in it. And the last technique is molten salt media cracking of methane. In this, what we do is a packed bed is taken in which molten salts are filled, and these from here methane is introduced, and methane gets decomposed by coming in contact with this hot molten salt bed. And due to the carbon produced, which has a lower density compared to this molten salt, carbon deposition problem is also solved. So due to the lower density, carbon gets comes up is settled from above, is removed from above, and hydrogen being a gas is taken out from above. So here carbon deposition problem is solved, but this technology is still under development. So theory part for today is this only. So let us come to some of the questions. Coming on to just a second. So the first question, typical composition of the LPG. Anyone? Hello, am I audible?
Yes, ma'am.
So do you guys, any one of you know the answer for this? So the answer to this is I have told that it is mainly LPG mainly consists of propane and butane, and the answer is 20% propane and 80% butane. The second question is match the following gaseous fuels with typical heating values. So as I have told earlier, LPG consists of the highest heating value, then the natural gas, and then the coal gas. So basically the natural gas is I guess, 41 and coal gas is 20. The next question, which of the following is or are considered as the property of gaseous fuel? Anyone? The options are octane number, Wobbe number, higher calorific value, and all of the above. As we have talked that octane number is also required here, we have seen that it is a property of gaseous fuel. Basically, it tells the anti-knocking property of the fuel. And Wobe number, it tells us the amount of heat released by a gaseous fuel per unit volume of the gaseous fuel. And the calorific value, it basically tells us about the heating value of our fuel. So basically, all these three are property of gaseous fuel. Question number 4. The Wobe index or Wobe number is expressed as. It is basically the gross calorific value in millijoule per meter cube upon relative density of air to the power zero point 0.5. So this Wobe number basically tells us about the amount of heat released per unit volume of the gas. So basically, if two gaseous fuel consist of this shows same Wobe index, then it can be replaced in a mixture of gases without hampering the quality of our gas mixture or without hampering the required energy, without decreasing or without hampering the amount of energy we require from that gaseous mixture or gaseous fuel. The fifth question is match the following technology with their hydrogen production efficiency. The answer to this is steam reforming. So gives a higher hydrogen production efficiency. As I told that the most used technique for hydrogen production is the steam reforming, steam methane reforming. Then the second one, biomass gasification. It gives hydrogen production efficiency of 35 to 50, but photolysis shows a very less efficiency of 0.5%. Another question, sixth question is important routes for hydrogen production. Thermolysis of water, electrolysis of water, dark fermentation, all of them. It is basically all of the above. All these techniques are used for the hydrogen production, but dark fermentation and thermolysis of water, they are not commercially used, but this electrolysis of water is commercially used. But all these three techniques are used in hydrogen production, and the commercial one is only electrolysis of water here. Otherwise, steam reforming and that the partial oxidation, they are also commercial, but here electrolysis of water is commercial. Moving on to the next question, the overall Fischer-Tropsch synthesis reaction is. The answer to this is it is exothermic in nature. Basically, all these options are exothermic, but the exact amount of heat is minus 180 kilojoule per mole. Identify P and Q in the following process. So this is basically the Fischer-Tropsch synthesis flowchart. So here it is Fischer-Tropsch reactor, FT reactor, and this one is distillation column. As we can see, different cuts of the liquid fuel are given here. So basically the answer is P is FT reactor and Q is distillator or distillation column. The ninth question is the favorable condition for steam reforming process. So steam reforming process takes place in the temperature range of 700 to 850 degrees C, as I have told, and the pressure of 15 to 30. What is the approximate percentage of world's energy consumption in terms of natural gas? The answer is 21%. 21% of energy, world energy consumption comes from natural gas. Let's come to one of the numerical question. The gas produced by a steam reformer is exiting at a pressure of 2100 kilopascal. It is basically given. So this here is the total pressure. Determine the partial pressure of each component. So mole fraction of different components, hydrogen, steam, carbon monoxide, carbon dioxide, and methane is given. This is the mole fraction given here, and partial pressure is asked. So what is the formula? It comes from the Dalton's law. Pi equals to yi into pt. Basically, this is pt. So this is the partial pressure of I in a mixture of different gases. So basically, we will be calculating it like this: 0.35 into 2100 is 735. 0.40 into 2100, which is 840 kilopascal. 0.15 into 2100 is 315 kilopascal. 0.06 into 2100 is 126. 0.04 into 2100, it is 84 kilopascal. So the answer is first one, which is hydrogen. Partial pressure of hydrogen is 735 kilopascal. Steam, it is 840 kilopascal. Carbon monoxide 315 kilopascal. Carbon dioxide is 126 kilopascal, and methane is 84 kilopascal. So the answer is first one. Coming on to the next question, which is hydrocarbon dew point is a function of dash and dash. It is basically a function of gas composition and pressure. Basically, the dew point may vary if the amount of gas composition, if suppose it is a mixture of gases, the the dew point for a definite mixture of gases may change if we change the gas composition into it and the pressure. Coming on to the 13th question, identify A, B, C in the given flow chart. Are these questions understandable to you? Hello.
Yes, ma'am.
You may ask if you have some queries in the middle. You may ask. So, the 13th question, we have to identify what is this unit A, B, and C. So, basically, it is the flow sheet for application of electricity production. Let me show you. We have talked about it. So, this flow sheet we are talking about. So, here this is given A, it is B, and this one is C. So, here it is steam turbine, which on expansion releases pressure, and boiler is used for heat recovery, and here CNG is introduced for into the combustion chamber for combustion. So the answer is steam turbine, boiler, and combustion chamber. So here A is boiler. Sorry. So this is coming on to the next question. Two major components of syngas. So this is very simple. The major components of syngas is carbon monoxide and hydrogen. In modern steam reforming process, catalyst uses, I have told during this steam reforming part, the catalyst use is nickel on ceramic support with or without promoters or stabilizers. Moving on to the 16th question, carbon monoxide and hydrogen ratio in autothermal reforming is around. It is 2. 17th question, which is reactions carried out in the reforming zone of the autothermal reforming reactor is. So in autothermal reforming reaction, basically it is a mixture of SMR and partial oxidation reaction. So in SMR, it is the reaction with steam, and in partial oxidation, it is in the presence of limited as well as excess oxygens. Sorry, just a second. Is there something wrong with the question, I guess? Sorry, guys, this question is steam methane reforming. So the reactions carried out in steam methane reforming is basically this one. In the presence of steam, reaction takes place. The next question is for low temperature Fischer-Tropsch synthesis process, methane number of the product is nearly. So in the low temperature, as I have told that the gasoline to diesel ratio, it is 1:2. So more diesel is produced. So basically here, cetane number is more at low temperature, which is 80. Question number 19. What product is taken out other than hydrogen in the pressure swing absorption process for hydrogen separation? It is basically tail gas. The mixture of all other gases in PSA, when this mixture of gases goes in, hydrogen is removed and the mixture of all other gases is basically it is called tail gas. Coming on to another similar kind of uh, numerical question. The gas absorbed by a steam reformer is exiting at a pressure of 2500 kilopascal. So basically, this is the total pressure, 2500 kilopascal. It reminds the partial pressure of each component. So these are the components given, and the formula of partial pressure is partial pressure equals to total pressure into mole fraction. So basically, we will be getting 0.392 into 2500, which will give us 980 kilopascal. 0.438 into 2500, which will give us 1095. 0.081 into 2500 will give us 202.5 kilopascal. 0.08 into 2500 will give 200 kilopascal, and 0.009 into 2500 will give 22.5 kilopascal. So the answer here correct is first one, which is hydrogen is 980 kilopascal, steam is 1095 kilopascal, carbon monoxide is 202.5 kilopascal, carbon dioxide is 200 kilopascal, and methane is 22.5 kilopascal. Coming on to one another numerical question and the last one for the day. Dry methane is bond with dry air. Both are at 25 degrees C initially. The flame temperature is 1500 degrees C. If the complete combustion is assumed, how much excess air is being used? The reaction is given here. This is the reaction. And the standard heat of reaction is minus 7.345 into 10 to the power 5 joule per gram mole of CH4 reacted. So it is basically the heat generated heat due to reaction. Mean molar specific heat of gases between 25 degrees C and 1500 degrees C are in joule per gram mole Kelvin. These are the mean molar specific heat of these gases are given in this table. So basically, we have to find out the excess percentage of excess air. So let us start. Let us assume Y number of moles of oxygen are present in feed. We are introducing, we are feeding air. So it will consist of 21% oxygen and 79% nitrogen, basically. Reference temperature here is 75 degrees C. And enthalpy at 75 degrees C of methane, oxygen, and nitrogen is basically zero. Because they are initially at 25 degrees C. So let us make a table. Let us make a table for both inlet and outlet conditions. Basically, the temperature of reactant basically is methane and air that is oxygen and nitrogen. So inlet temperature is 25 moles of methane. It is basically, let us take 1 mole of methane is taken in the feed and Y moles of oxygen is taken. So if 21 moles of oxygen contains 79 moles of nitrogen in air, so Y moles of oxygen will contain 3.76 moles of nitrogen, 3.76 Y moles of nitrogen. So 3.76 Y moles of nitrogen are present in the feed, in the inlet. Enthalpy of all the of the reactants will be zero. Outlet temperature is 1500. All the reactants and of all the products and leftover reactants. Moles left of methane in outlet is zero. As we can see, there is no methane in the in the product part. Moles left of oxygen is basically Y minus 2 because for 1 mole of methane, 2 moles of oxygen are used. So total moles for Y in the feed. So we will reduce if we take 1 mole of methane is consumed. So 2 moles of oxygen will be consumed. So it is Y minus 2. Nitrogen is unreacted, so it will remain same. 1 mole of carbon dioxide is formed from 1 mole of methane and 2 moles of steam from 1 mole of methane. So enthalpy will be taken by MCP delta T. So it is CP delta T. M is here. So basically enthalpy it will be just a second. So CH4 is not present in the product, so it is no enthalpy. For oxygen, it is 34.01. For nitrogen, It is carbon dioxide is 51.88 into 1500 minus 25, and for steam it is 40.45 into 1500 minus 25. So let us do a enthalpy balance. Basically, energy balance we are doing. It is accumulation of energy equals to input minus output plus generation of energy if some kind of reaction is taking place. So which is given in our question. So input energy is zero, as we have seen. Oxygen, this is M into Cp of oxygen plus moles, yani M of nitrogen into Cp of nitrogen plus M of carbon dioxide into M is of carbon dioxide is 1 mole. So Cp of carbon dioxide into M of that is 1 mole of carbon dioxide. Then of hydrogen, Cp of hydrogen into M of hydrogen, which is 2 moles, and overall taking the temperature difference. When heat generation is given in the question, it is minus 7.345 into 10 to the power 5. So it will be minus 7.345 into 10 to the power minus 5. So after solving this equation, we will get y equal to 3.6276 moles of oxygen. So y is 3.6276, which is we can say that 3.6276 moles of oxygen are fed into the reactor. So percentage excess we can calculate, as we have seen here that 2 moles of oxygen are used. In the equation we can see in the reaction 2 moles of oxygen are used. So excess oxygen upon 2 into 100, which will give us 81.3% excess oxygen. So the answer is 81.3%. So this is the last question for today. Is this clear?
Yes, ma'am. Can you please do question 11?
Okay. This is the question 11.
18, 19, 20 also, please.
Okay. These are 18 and 19.
Okay.
And this one is 20.
Okay.
Any other questions?
No.
So should we end the class for the day?
Okay, ma'am.
Okay then. Thank you everyone. You may leave the class.